Hi guys, Mr. Kane here.
Hi, my name is Finnegan Kane.
Hi, I'm Liam Kane.
And we're here today to talk to you about valence shell electron pair repulsion geometries. If you remember the handout, there are 15 unique geometries on this handout. The thing that you need to remember though is that it's really important to know these 5 orientations. These 5 orientations lead us to all 15 of the unique geometries. So we've got the linear, we've got the trigonal planar, the tetrahedral, the trigonal bipyramidal, and the octahedral. And as you can see here, they compare steric numbers here, which is basically just how many bonded pairs or lone pairs that are attached to your central atom. The linear has 2 bonded pairs. The trigonal planar has 3 bonded pairs. The tetrahedral has 4 bonded pairs. Trigonal bipyramidal has 5 bonded pairs, and the octahedral has 6 bonded pairs. The idea here is that valence shell electron pairs repel each other. So in other words, this pair of electrons attached to the left x and this pair of electrons attached to the right x are repelling each other. Because this is a 3D structure, these 2 pairs have to get as far apart from each other as possible. That means that they're going to be 180 degrees apart from each other. If we have something like a trigonal planar, then we wind up having 3 bonded pairs to the central atom. These 3 bonded pairs push each other equally, and as you know from your geometry class, a circle is a full 360 degrees. 360 divided by 3 is?
120.
120 degrees. Okay. Now, that is the orientation and a geometry, trigonal planar. If we modify one of the bonded pairs and turn it into a lone pair, that changes things a little bit. It turns out that this lone pair pushes out just a little bit more than a bonded pair. Okay? That means that the angle between the 2 bonds here isn't quite 120. It's something a little bit less. We're not going to worry about the exactness of the angle in this class. We just need to realize that it's less than 120 because we want to make sure that we understand that this lone pair pushes harder than a bonded pair. So I think it would be useful to take a look at the 3D structure for each of these. Okay, we're going to start with a single atom that we're going to bond another atom to. This is a no-brainer. We've got 2 atoms, connect them with the shortest distance possible, and you've got something that's linear, a straight line. Okay. If I add another bond, you notice the reflex there right away. So this is an electron pair here that's in the bond to this atom, and this is an electron pair here that's bonded to this atom. Notice when I try and bring them together, they naturally want to migrate apart, and they do so in such a way that makes it 180 degrees apart, an exact straight line. If I add another bond domain, we wind up getting 3 domains. You'll notice that this is completely flat. It is a planar molecule. What kind of planar molecule is trigonal? Because there's 3 angles here. Now, I can remove that bonded pair and I can change it to a lone pair and check out what happens here. Okay? That changes just ever so slightly the geometry here. We only really pay attention to the atoms. We don't pay attention to the lone pair. So we wouldn't call this trigonal planar anymore. We would focus on these 3 things. So we say it looks a little bit bent. If I remove the lone pair and I add in another bonded pair, I get a steric number of 4. This has 4 bonding domains, and we call this a tetrahedral. Mostly because if you connect these 3 atoms, you get a face. If you connect these 3 atoms, you get another face, and if you connect these 3 atoms, you get another face, and another face over here. This is a tetrahedron shape when you talk about geometry class. The bond angle here is about 109 degrees between one atom and the next. If we substitute out one of the bonded pairs for another lone pair, we wind up with this shape. Again, we don't pay much attention to the lone pair here. It is important to note that this lone pair pushes down on these three terminal atoms on the outside. That means that it's not planar anymore. This looks a little bit more like a trigonal pyramid. Trigonal because there's three atoms bonded to the central atom, and a pyramid because it looks pyramidal. We could also take away another bonded pair and replace it with another lone pair. Okay? This gives us a different geometry. It's no longer trigonal. Now it's bent again. But notice that this version of bent has two lone pairs instead of three lone pairs. Going back to steric numbers, we remove the two lone pairs and add in a total of 5 bonded pairs. If you're looking at your geometry handout, it looks a heck of a lot like this. This is called trigonal bipyramidal, or some people like to call it trig-bippy. I like trig-bippy. Okay. The reason why you're getting trigonal bipyramidal is because if you connect the edges of all three of the central atoms around the equator here, and you make them connect with the top here, you get something that looks like a triangle pyramid, three-sided pyramid. On the bottom, you also have a triangle pyramid if you connect all of the atoms and the faces together. So we call it a trigonal bipyramidal. The three atoms around the outside, notice, on the equator, are 120 degrees apart from each other. These two atoms are 90 degrees apart from each other. If we remove one of the bonded pairs and replace it with a lone pair, we get something called the seahorse or the seesaw. And in order to make it look like it does on your handout, I'm going to have to rotate it a little bit like, pretty much like this. Ooh, it's getting crazy and wild. Oh, there we go. I think I got it. That's pretty close to what it looks like on your handout. Again, the three atoms that are lined up in a row are forming a linear, so 180 degrees. These two atoms around the central hub are less than 120 degrees apart from each other because this lone pair is pushing harder on them, causing them to be slightly closer together. This angle is a bit more than 120. Okay, if we remove one more bonded pair and replace it with a lone pair, still having a steric number of 5, I'm trying to rotate this around to the way it is on the geometry handout, we get something that's pretty much T-shaped, and this is more or less going to show you the T-shape. Yes, I'm sorry, the T-shape is sideways, but we're just going to have to deal with it. What that means here is that we got a 90-degree angle here and a 180-degree angle between these atoms. Okay. Oh, and it has shown up, and you can hear him chanting in the background. All right. What we're going to do now is we're going to take off one more bonded pair, and we're going to replace it with a lone pair.
Again.
This is going to give us linear, because the three atoms are lined up in a straight line. And there are 3 lone pairs around the equator here. These 3 lone pairs should be about 120 degrees apart from each other because they're representing a trigonal planar sort of orientation with each other. All right, only one more part of the chart left to go, and that's the octahedral, which means we have to get rid of our 3 lone pairs and add in 3 more bonds plus 1. So we have a total of 6 bonded pairs. This is the octahedral, and I'm just going to try and get it to move around so that it looks like it does on the handout. This is pretty gosh darn close. There we go. That looks about right. And this is the octahedral orientation. Okay. Now, the octahedral orientation has 90 degrees between any 2 atoms that are close to each other here. Okay. So since We've reached the limits of our steric number here. We can't bond more than 6 things to the central atom. I'm going to take away one of the bonded pairs, and I'm going to replace it with a lone pair. If I arrange this similar to how it is on the handout, you wind up seeing something like this. The lone pair is on the bottom. The rest of the atoms are on top. This forms a square pyramid because if I connect these 3 atoms together, I see a face that looks like a triangle. There's a total of 4 of these faces, which is why we call it a square pyramid. The next thing we want to do is we want to remove one more bonded pair, and we want to add in a lone pair again. Okay. Now those 2 lone pairs naturally push on each other really hard and don't want to be anywhere close to each other, so they're going to be 180 degrees apart. The way it looks on our handout is a little bit like this. Notice that these 4 atoms around the equator have to be 360 divided by 4. And 360 divided by 4 is
90!
all right. Wow. And let's see. We need to take away another bonded pair and replace it yet again with another lone pair. Those 3 lone pairs are pushing pretty hard on each other. Our packet looks a heck of a lot like this. You'll notice that the 3 atoms in a straight line here form 180 degrees. These atoms here are forming a 90-degree angle. Lastly, what we need to do is we need to remove one more bonded pair and add in one more lone pair. That makes us look like this, which is linear. The 3 atoms are straight in a line. The 4 lone pairs on the equator are all exactly 90 degrees apart from each other. Okay? That's a quick tour of all 15 of our geometries, and you might have noticed that some of the geometries have the same name.
Yes, you might have noticed that.
All right, guys, that's it for tonight. My helpers, Finn and Liam, are probably getting ready for going to bed, and they've had a tough day of e-learning too. Hope that today's not too bad. Don't forget, there are office hours, and we'll check in together pretty soon. All right?
Bye!
Have a great day tomorrow and good night.